Hello everyone, welcome back. Today I will be discussing the third problem from the Contains Duplicate series. Leetcode 220 contains duplicate 3. I have already covered contains duplicate 1 and 2 in my previous videos and have added the links in the description below. If you haven't solved contains duplicate 2, I strongly recommend watching or solving that one first. It will make this problem much easier to understand as its solution builds directly on the concepts from that problem. In this problem, we are given an input array and two additional parameters, index difference and value difference. So given these three inputs, we have to find a pair of indices ij such that these three conditions are met. First is I not equal to j. This means that the element at the same index cannot be considered a duplicate of itself. The next point is absolute value of I minus j should be less than equal to index diff. So what is index diff here? Index diff is basically the k or window size as we discussed in the previous problem. That is, it defines what we consider as nearby in this problem. For clarity, let's refer to it as k. This means the pair of indices that we will find should be at most at k distance from each other. Now the third point is absolute value of nums of I minus nums of j must be less than equal to the value difference. So what does value diff mean? Value diff defines what we actually consider as duplicate, or more precisely an almost duplicate in this question. If you remember, in contains duplicate 1, we were looking at exact duplicates in the entire array. In contains duplicate 2, we looked at nearby duplicates within a window of size k. But here in contains duplicate 3, we are looking for almost nearby duplicates within a window of size k. So what does almost mean here? In this problem, two values are considered duplicates if the absolute difference between them is at most value diff. For example, if we have a value diff of 0, then this problem becomes same as contains duplicate 2. That is, in this case, element 1 will be a duplicate of another element 1 if both are at most k indices apart. But if the value diff is 1, then the elements 1 and 2 can also be considered almost duplicates of each other because they have the difference of 1. However, we need a general solution that works for any given value diff as per the constraints. The brute force solution for this problem is quite simple. We scan through the input array and for each element we compare it with the next k elements to check if the pair of the current number with any of these k numbers has an absolute difference less than equal to the value diff. In other words, we are searching for the almost duplicate of each element within the next k elements. So for every one of the n elements, we are doing k comparisons, which makes the overall time complexity O of n into k. And since k can go up to n, so the worst case becomes quadratic in nature, which is too slow for large inputs. The only good thing here is the space complexity is just O of 1, as we are not using any extra data structures. So now, what if instead of the brute force approach, we use a sliding window technique? Say, while scanning through the array, we keep track of the last k elements in a window. And for each new element, we look up whether there is an almost duplicate in the window. That is, we look for any number in the window which satisfies the absolute difference less than equal to value diff condition with the current num. But will this help? It turns out not really, at least not with a normal sliding window. And here's why. In the contains duplicate 2, we were only checking for exact duplicates. This meant we could have simply used a set for the sliding window and then check the existence of the exact duplicates in the set in O of 1 time. But here in contains duplicate 3, we are not looking for exact match. Our target can be any number with the difference of plus minus value diff. So a simple O of 1 lookup from the set will not work, and we would still need to search through all the k elements in the window to find a valid number. And for each of the n elements, if we do a linear search within the window of size k, it again takes O of k time per element, which means the overall time complexity is still O of n into k, which is no better than the brute force. So the real question is, can we make this search any faster? Think about it. If we keep all these k elements in sorted order, then instead of doing a linear search, which takes O of k time for k elements, we could do a binary search which is much faster. Binary search on a sorted structure with k elements takes only O of log k time. So if we maintain a sorted sliding window of size k, we can significantly speed up the search. And this is where a special data structure comes in handy. In Python, we can use a sorted set for this purpose from the sorted containers module. A sorted set keeps all the elements in sorted order while still allowing efficient insertions and deletions, which both works in log k time for a sorted set of size k. And if you are coming from other languages, you can think of sorted set as being similar to a tree set in Java or std set in C++. The sorted property is exactly what we need because it allows us to quickly find if there is any number in the window that lies within our desired range using binary search. So let's quickly go through this example to understand the flow better. So this is our window which is initially empty and will be implemented using a sorted set. So all the elements within this window will be in a sorted order. So to keep track of the oldest element that was added to the current window, we will use a pointer called left, which will initially point to the index 0. So this is our left pointer. Now we'll iterate through our input array using another pointer. Let's call it right. And the difference between the left and right will comprise of our current window. So initially right is at index 0, which is pointing to the element 1, and we can see that there is no element present in our sorted set yet. So we'll simply add 1 to our window and move our right pointer to the next element. We are using right pointer as the iterator. So now our right is at index 1, which is pointing to the element 3. Now we will check if there is any element in our window which falls in the plus minus value diff of 3. This implies within the range of plus minus 1 from 3. And we can see that there is no such element. So we will just add 3 to our window. So currently our window size is 2 and we will move our right pointer to the next element. So right is at index 2, which is pointing to the element 5. So now we will check if there is any element in our window within the range of plus minus 1 from 5, which can be either 4 or 6. And we can see that there is still no such element. So we will simply add 5 to our sorted set. But note that now our window size is 3, which does not follow the less than equal to k condition. So we need to slide our window. And how we will do it? We will just go ahead and remove the oldest element that we added to our window. And for tracking that, we are already using our left pointer. So we'll simply remove the element pointed by our left index from our window. So in this case, we will remove 1 and then shift our left pointer by 1. So now our left is at index 1 and our current window contains these two elements. Finally, we will iterate to the last element. So our right pointer will move to index 3, which is pointing at 6. So in this case, we will check if there is any number in our window within the range of plus minus 1 from 6. And we can see that there is an element 5 which falls within this range. So we have found a valid pair and we can return true. And even after going through the entire array, if we haven't found a valid pair, then we would have returned false. Note that from an implementation perspective, when we are searching for a number x that satisfies the almost duplicate condition or the plus minus value diff condition, it actually means this equation, the absolute difference of the current number and the value x must be less than equal to value diff, which we can easily rewrite as the current number minus value diff less than equal to x, which in turn is less than equal to current number plus value diff. This is just basic arithmetic. So first we will quickly do a binary search to find the smallest number x that is greater than equal to number minus value diff in the sorted window. And if that number exists and it is less than number plus value diff, then we have found a valid pair. Apart from this, there are two edge cases we need to be mindful of during interviews. The first is if k is less than equal to 0, that is the index diff is negative. This is an invalid case as it means we cannot compare any two different elements because even the closest pair has at least a distance of 1. So no valid pair can ever satisfy this condition. The second is if value diff is less than 0. This is also invalid because value diff represents the maximum allowed absolute difference in a valid pair and absolute difference can never be negative. So no pair can ever satisfy this condition. So in both of these cases, we can simply return false as these are invalid scenarios. However, for this specific Leetcode problem, the constraints given already exclude these cases. So we don't need these extra checks here for our code to pass on Leetcode currently. But in an interview setup, it's always good to clarify these constraints with the interviewer upfront before jumping into the solution. Now let's analyze the time and space complexity. So we have our window as a sorted set and each insertion or deletion in a sorted set of size k takes O of log k time. Similarly, each search within the window also takes O of log k time as we are using binary search. And since we do these operations for all the n elements, so the overall time complexity becomes O of n log k. And the only extra space that we are using is for the sorted set, which stores at most k elements. So the space complexity becomes O of k. So this is a perfect example of time-space trade-off. Here we are saving time using a smarter data structure, but at the cost of a bit more space. Now let's quickly code this up. So from the sorted containers module, first we will import the sorted set data structure. From sorted containers, import sorted set. The sorted containers is a Python module that provides efficient sorted data structures. Next we will use a sorted set to create our window. So window is equal to sorted set. Also we will keep our left pointer at 0 as we discussed earlier. Now we will scan through each element in our input array. So for num in nums, you can think of num as the element at the right pointer. Next we will use binary search to find the position of the smallest element in our window, which is greater than equal to num minus value diff. For this we will simply use the bisect left method from the bisect module, which is the inbuilt version of binary search. So position is equal to window dot bisect left of num minus value diff. The bisect left method returns the leftmost position for our requirement, which implies it will return the index of any number which is greater than equal to num minus value diff. But note that if no such element exists in our window, then bisect left will return the index after the last index, which will technically fall outside our window. So we need to verify that the position returned by the bisect left is valid or not. For that we will check if position less than length of window, and if it is, then we will go ahead and check the next condition, that is the value at this position window of pause is less than equal to the current number plus value diff. This is the exact same condition that we derived during our explanation. And if we are able to find a position which satisfies both these cases, in that case we have found a almost nearby duplicate and we will return true. Otherwise we will go ahead and add the current element to our window. So window.add num, and after adding the current element, if our window size, that is length of window, exceeds the k value or the index diff, in that case we will slide our window. That is, we will remove the oldest element, that is the element pointed by the left pointer, from our window. So window.remove nums of left, and we will shift our left pointer by 1. And after scanning through all the elements, if we haven't found a valid pair yet, then we will return false. This was all the code that we needed to solve this problem using sorted set sliding window. Let's run this. We can see that this is accepted and is working fine. This is a fairly hard problem, and if one can come up with this sorted set based solution in an interview setup, it's good enough in my opinion. It naturally extends the solution for contains duplicate too, which makes it a bit easier to come up with. But there's an even more optimized approach that uses bucketing and runs in O of n time. But even though it's more optimal, it's also harder to derive in an interview on the spot. But if you are curious and want to check out the bucketing solution as well, I have included both the approaches on my website DKodeTree.com. I have implemented the bucketing method also in a way that feels conceptually similar to the sorted set approach so that it becomes easier to follow. And if anything feels unclear or you'd like me to create a separate video explaining the bucketing solution step by step, just let me know in the comment section. So this wraps up the contains duplicate series. Next we will move to the 2-sum extended series and resume with the 3-sum problem. I have already uploaded the videos for 2-sum and 2-sum 2, and I highly recommend watching those first, as understanding the 2-sum 2 will make the 3-sum problem much easier to grasp. If you enjoyed and learned something new, be sure to hit the like and subscribe button and tap the bell icon so that you won't miss what's coming next. Your support means a lot and keeps me motivated to share more content like this. Thanks for watching. See you in the next video.